Hello everyone, welcome back again to this online course on fundamentals of composites and cellular materials. So, today's focus would be on the topic of advanced processing techniques and examples. For the last few classes, we are discussing on this particular topic of advanced composites. Now, this topic of advanced composites we have divided into 4 classes initially. The first one is advanced metal matrix composites, then comes advanced ceramic matrix composites, and these 2 topics have already been discussed in details with examples and case studies. And for the last class, last couple of classes in fact, we are discussing on the third topic, which is advanced processing techniques for advanced composite synthesis and fabrication. And in this, we have discussed first on the topic of spark plasma sintering, an advanced sintering technique which is being used heavily for last 10 years I would say, and we have talked about different case studies as well in this on SPS. And in the last class, I have explained about the basic mechanism in microwave sintering, and in today's class we will discuss certain examples. So, let us begin our class today with these examples. The first example or the case study which I would like to portray here is a composite material. It is a ceramic composite where the matrix is ZrB2 and it is reinforced with B4C particles. Now, the importance of ZrB2 is that it is having very high melting point, it has definitely high strength. Along with these 2 attributes which most of the ceramic materials would be having, ZrB2 is also having, or ZrB2 also shows good electrical conductivity and excellent chemical stability. And because of these attributes, ZrB2 finds application in thermal protection systems, cutting tools, high temperature electrodes, molten metal crucibles. So, all high temperature application, as you can see on these application areas ZrB2 is used or can be used. However, the basic problem of ZrB2 is that it is difficult to densify, because ZrB2 particles will be having some amount of very thin layer of oxide on it, and that actually hinders its densification. Okay. So, in today's class we will use microwave sintering to densify ZrB2. So, let us see how the material could be prepared. You can see matrix ZrB2, the particle size in the range of 20 micrometer initially, and then it has been attrition milled for 2 hours to reduce the particle size. Similarly, the reinforcement particles are B4C around 0.8 micrometer. Again, this has been ball milled for 24 hours just to reduce the particle size. As we reduce the particle size, it will be difficult, it will be easier to sinter them, and then this B4C and ZrB2 has been mixed in certain proportions again in an attrition mill. Okay. The next step, once the powder mixture is prepared, the next step was cold isostatic pressing. So, green compacts are basically prepared at a very high velocity. Okay. Now, cold isostatic pressing means the powder particles are compacted heavily, however, those are not sintered. So, once this cold isostatic pressing or CIP is done, then these green compacts or the pellets are now subjected to microwave sintering, okay, in argon atmosphere. And once the microwave sintering is done, then different characterization has been carried out on these samples. The microwaves during microwave sintering, the temperatures, as you can see, 4 temperatures were considered, starting from 1630 degrees Celsius to 1920 degrees Celsius. All right. Now, if you look at the initial densification study, you can see here that if you compare with the conventional sintering, which is shown in black color, and then the red one actually is for microwave sintering. So, you can see at lower temperatures microwave sintering is showing higher densification than conventional sintering. So, if I do not want to go for high temperature sintering, at lower temperature microwave sintering is definitely superior in terms of densification if you compare with conventional sintering. However, at high temperatures both are having quite good densification, both in case of microwave sintering and conventional sintering. Okay. Now, if you look at the microstructure, what you see here is that there are 4 different temperatures from 1630 to 1720 B, and then C is 1820 and third one is 1920. Okay. So, with increase in temperature of sintering, what can be observed that the pores which you can see here clearly at lower temperature, those pore size is getting lowered, and also the number density of those pores are getting minimized, or in other way we can clearly say that the volume fraction of the porosity is getting reduced obviously with increasing temperature. Another very interesting fact you can see here is that even there is increase in temperature, however, as the time of sintering is not very high. So, you can see initial temperatures up to 1820 there is hardly any grain growth. Okay. It almost remains same to at 1720 it is again remaining the same, and then there is slight increase in grain size at 1820. Okay. So, one thing we can clearly say from here, or basically one big advantage here is that with increase in certain temperatures there is increase in densification without any appreciable growth in the grain size. Okay. So, as I was mentioning earlier, grain growth was minimal for microwave heating, relative density increasing from 88% to 98%. So, initially if it was the green compact was 88%, and then actually that increases even more than 98%, which is very good densification. So, microwave sintering promoted densification of this particular composite material without significant grain growth, which I was trying to impress upon. Okay. Now, if you look at the mechanical properties of these composite materials after this, after we understand that how this can be sintered. So, in this particular case ZrB2 B4C particle mixtures were sintered by microwave sintering at different temperatures, and then we observed the effect of this microwave sintering plus sintering at different temperatures, the effect of that on the microstructure. And now, if you look at the mechanical properties, so in this graph both hardness as well as fracture toughness have been plotted for this composite material at different temperatures. Okay. So, you can see MS 1630, MS 1720, MS 1820, MS 1920, these are the sintering temperatures during microwave sintering. Now, with increasing temperature, what is very clear here, if you look at the hardness data, there is increase up to 1820, there is increase in hardness. Okay. Now, why the hardness is increasing? There are a couple of reasons. Number one reason, obviously there is more densification. With increasing temperature, the porosity volume fraction is going down, as we have observed. Both the porosity size and the number density of porosity is getting decreased, and obviously that is having a direct effect on the hardness is increasing. Along with that, another factor is also there, which sometimes we undermine, is the grain size. What we observed till 1820, there is not much increase in grain size, or basically grain size is remaining almost similar. Okay. So, that is why because of this small grain size, again the hardness is increasing. So, there are both the reasons are there. First one is obviously densification, second one is the grain growth restriction, which is also playing a good role here, because what we are seeing here is that beyond 1820 there is decrease in hardness. Now, this is something we need to understand, why the hardness is decreasing even after increase in sintering temperature, which basically leads to better densification, as we understand. What is happening here, if you remember earlier, we showed in this particular table is that there is certain amount of grain growth beyond 1820. Okay. That is one factor, that there is grain growth which could lead to decrease in hardness and strength. But not only that, what happens actually, if you are going at a higher temperature and then you see there are two different phases, one is ZrB2, other one is this before C particles. Now, before C particle and ZrB2 particles being two different materials, they have certain difference in their coefficient of thermal expansion, which we term as mismatch in CTE or mismatch in coefficient of thermal expansion. Now, when you raise the temperature to a very high temperature, this difference, obviously, when there is a difference in coefficient of thermal expansion, during cooling there will be residual stress generation at the interface, is not it. Now, if the temperature of sintering is higher, then the temperature difference during cooling is obviously higher, and that leads to even higher amount of residual stress. So, we can say as we increase the temperature at the interface, there will be higher amount of residual stress, and this residual stress, as the residual stress crosses a limit, crosses a critical value, it would lead to delamination at the interface or cracking, formation of fine cracks or micro cracks at the interface in this material. So, again if you look at this hardness data, there are two things happening. Number one is that there is increase in grain size. However, along with that also there is actually formation of micro cracks because of the residual stress at that high temperature cooling. Okay. Because of these two reasons, the hardness is now getting decreased. Okay. So, initially hardness increases, and that is because of better densification and restriction in grain growth. Then the hardness is decreasing, and that is happening because of increasing grain growth. Along with that, there will be formation of micro cracks, which would actually hamper the mechanical property, the strength, hardness. All right. I hope you understand this point. Now, if we look at the fracture toughness data, we see that even there is increase in densification, increase in sintering temperature, which is leading to increase in densification, but fracture toughness is not increasing, but actually it is decreasing. Okay. So, one thing can be said here is that in earlier cases we discussed about different ceramic matrix composites, and in few instances we showed different kind of phenomenon like crack bridging, crack deflection, crack branching, delamination at the interface, few things we discussed, which actually leads to improvement in fracture toughness in ceramic matrix composites. Those phenomena or those factors are not happening here, not playing a role here. That is why fracture toughness does not get improved. Another factor is also there along with this. As I was mentioning that let me just say it once more, is that improvement in fracture toughness in ceramic matrix composites takes place because of few phenomena. It could lead to delamination at the interface, there could be crack branching or crack bridging, there could be also the crack could be tortuous, or ultimately the crack could be lead to branching. Okay. So, because of all these things, there is generally improvement in fracture toughness in ceramic matrix composites. Those things are not happening here clearly, and because of this, that fracture toughness is getting reduced. There is another factor with that which I need to emphasize, is that what we observed, that with increase in temperature there is densification and porosity gets reduced. Now, in some cases there are examples where if there is porosity, in fact there are microporosities, those microporosity helps in improving fracture toughness, because that actually accommodates certain amount of deformation, okay, and actually improves the fracture toughness. However, as the porosity is getting reduced, that could be playing a role in decreasing the fracture toughness here. So, decrease in porosity in this case could lead to decreasing fracture toughness as well. So, both the factors are playing role here. The number one is decreasing porosity, and second one, as I mentioned earlier, is that the classic phenomena which takes place in ceramic matrix composite like interfacial delamination or crack bridging, crack branching, all these things are not happening here, and that is why the fracture toughness is getting reduced. Okay. So, we discussed about this one is about ceramic matrix composite which has been sintered or which has been made by microwave sintering. Okay. Let us take an example where metal matrix composites could be also made by microwave sintering. Okay. In this case, the matrix is copper, as you can see from here, and reinforcement is CNT particles, carbon nanotubes. Okay. So, what has been done in the processing steps? If you look at this particular cases here, so what you see here that CNT has been made by chemical vapor deposition. Okay. Once it has been made by chemical vapor deposition, this CNT was subjected to acid treatment. Now, I have mentioned in few classes earlier that why do we do acid treatment for like this kind of graphene allotropes like CNT or graphene nanoplatelets or graphene oxide particles, graphene oxide nanoparticles. The reason is that because of acid treatment there will be etching on the surface. So, that actually improves micro roughness on the surface. Along with that also, which is more important, is that the surface get functionalized. Functionalized means different kind of functional groups like COOH or hydroxyl or carboxyl, which basically contains oxygen atoms. So, oxygen atom containing functional groups gets attached on the surface of CNT, and those functional groups actually increases the homogenization or improves the homogenization of the CNT particles when they are getting distributed or when mixed with some other particles. Okay. So, there will be repelling action between these functional groups being the similar functional group. So, they will repel each other, that means the CNT particles will pushed from each other. Also, these functional groups helps in improving the wettability when these are mixed with other matrix material. Okay. So, what you see here is that so once this has been done, once the CNT has been functionalized, then it has been the CNT has been sonicated with copper acetate. Copper acetate is being used, it is basically a source of copper ion. Okay. So, basically that is what it says, CNTs and copper ion precursor has been sonicated. After this, once it is mixed nicely with the copper acetate, once the CNT gets mixed homogeneously, then the precursor would be vaporized, or basically the solvent gets vaporized and then it is dried and calcined at air. So, that you get a mixture of CNT with copper oxide. Now, the whole idea of using copper acetate or basically copper ion precursor here is that there is molecular mixing between copper and CNT. Just to improve the homogenization, just to improve the wettability, this particular step was done here. Okay. So, once it is calcined in air, then you have a mixture of copper oxide and CNT, and then as you can see here, there is a molecular level mixing of CNT copper powder was obtained after reducing the CNT CuO powder mixture in hydrogen atmosphere. So, once you get the CNT CuO powder mixture, it will be subjected to reduction in hydrogen atmosphere, and that would lead to a molecular level mixing of CNT Cu particles. So, now you have nicely mixed CNT Cu powder mixture, then it will be cold isostatic pressing, subjected to cold isostatic pressing, and it will be basically a green compact will be made at a very high pressure around 300 MPa, and then this green compact or cold isostatically pressed compact will be subjected to microwave sintering. And after doing microwave sintering, to improve further the densification, cold rolling has been carried out. Now, one question could come in your mind, that we talked about when we were talking about microwave sintering, the basic mechanism of microwave sintering, we were talking about dipole rotation and ionic conduction, which leads to the heat generation. So, what about metallic powders? Metallic powders or metallic materials would definitely not be having dipoles or ionic conduction kind of thing cannot be happening there. There also, but still in metallic powders also sintering could be taking place by microwave sintering. There are other factors like eddy field current and magnetic permeability. So, there are certain factors which could help also in case of metallic powders if the particle size is quite small. If the metallic particle size is quite small, then they will be able to absorb microwave energy and will get sintered. So, in this case you can see the Cu particles are quite small, because they are made by this kind of aqueous route. So, that is why it will be having good densification through microwave sintering. All right. So, now let us look at the powder mixture first, and then we will see the compact. Again, two cases have been shown here, 0.5 weight% and 1 weight%. Okay. And if you look at this TM image, it shows how nicely or homogeneously the CNT particles and the copper particles are distributed together. Okay. That is what they are calling as molecular level mixing. Okay. You can see here all the CNT particles and Cu particles are kind of separated out and distributed evenly. Okay. And you can see here this is 0.5 and 1%. So, obviously, as you increase the amount of CNT loading or CNT content, now here in 0.5% you can see those CNTs are residing nicely on the surface of the copper particles. Okay. However, when you have more amount of CNT, what you are seeing is that there is agglomeration, which is not very clearly shown here, but this area actually shows that there is certain amount of agglomeration of carbon nanotube particles. All right. Now, if we look at the densified microstructure, as you can see that with increase in CNT, the different microstructures have been shown A, B, C and D. So, 0.5 to actually 3.8%. So, obviously, 0.5 shows very nice compact, not any kind of porosity being observed on the surface. Okay. But there are a little bit of very minor or micro porosities, but as you increase the amount of CNT, you can see the porosity volume fraction is increasing. The porosity size and the numbers of porosity are increasing to a very high level as you increase the amount of CNT, and that is happening because of the agglomeration problem, which I have discussed a number of times in my class, that if we have nanoparticles and if we have too much of nanoparticles as reinforcement, it will be extremely difficult to disperse them evenly in the microstructure. Okay. And in fact, you can see the D image, which is basically with 3.8% CNT, a higher mag image has been shown here, and you can see that at those inside those porosities actually there is a lot of CNTs there. So, you can see CNTs have got agglomerated, and that actually led to porosity entrapment in between the particles of the copper. Okay. Okay. Now, let us look at the after the compact structure, it was rolled now. So, these images what you saw are microwave sintered and then it has been rolled. So, now this is both 0.5 and 1 weight percent has been rolled, and what you are seeing here is that in case of 1 weight percent, so 0.5 weight percent shows normal microstructure after rolling, you do not really see any porosity or any kind of defects, but what you can see here at 1 weight percent, you can see there are certain amount of cracks. So, there are porosities, and when the rolling was done, that loading led to this kind of crack generation or crack formation in case of 1 weight percent CNT reinforced composite. Okay. If we look at the densification data, so this line, the below line is for sintered composite. So, obviously, as we increase the amount of CNT, the densification is getting hampered. So, density is going down, densification is going down because of the agglomeration problem. However, that when it goes for, so if you compare these two data, the first two data which is basically for 0 weight percent or 0.5 weight percent, in both cases you can see the densification is better in case of rolling, after rolling. So, after rolling, once the rolling was done, obviously it led to improvement in densification. Okay. But still you can see that in case of rolling also you can see that as you increase the amount of CNT, there is slight decrease in the densification. So, that is bound to happen, but one thing is very good I would say is that after rolling densification has improved. So, now let us look at the mechanical properties. Okay. So, now if you see again, I do not have to really explain these things, but let me just mention it that if we see the lower curve which is basically for the sintered composite. So, you can see with increase in amount of CNT up to 0.5 weight percent, there is increase in micro hardness, and you also can see there is increase in strength. It is very clearly you can observe that there is increase in strength, there is also increase in both yield strength and tensile strength along with hardness. Okay. And that is happening because of the effective reinforcement being given by carbon nanotube particles. Okay. However, as you increase the amount of CNT content, obviously there is decrease in micro hardness, and also you can see there is decrease. So, this is for rolled structure, there is decrease in what do you call it, decrease in tensile strength, as well as the yield strength is not getting affected that much, but ultimately the tensile strength, the UTS is getting lowered. And you can see also with increase in the amount of CNT, there is continuous decrease in elongation, and that is obviously going to happen because CNT would be leading to decrease in ductility, okay, to some extent. Now, again you can see here that if you look at this particular data, that obviously with after rolling there is increase in the micro hardness data or the micro hardness values. Okay. So, now few things are happening here, I think you can explain, but just still let me just mention here that why the hardness is increasing. Hardness is increasing because of the densification number 1, sorry, not densification, but the increase in amount of CNT. So, CNT reinforcement gives good composite strengthening, and it could be leading to also some kind of dispersion strengthening, okay. And also CNT would actually restrict the grain growth, okay. So, that also helps in improving mechanical properties, as we are seeing hardness, tensile strength, all these things are improving. Okay. So, as it says ultimately that sintered composite hardness increases, CNT, there is good CNT copper interface. Yes, there is another very important point here is that as we have seen earlier, that there is molecular level mixing of CNT and copper. So, there is homogeneous mixing. Along with that, Cu is growing on the surface of CNT. The way copper was synthesized from copper acetate to copper oxide to ultimately elemental copper. So, basically it is basically growing on the surface of these CNT particles. So, that is again good, because actually that leads to improvement in the interfacial bonding. It improves the wettability. All right. So, that is one of the reason it says that good CNT copper interface and grain growth restriction, as I was mentioning earlier, that ultimately would lead to increase in hardness. However, increase of the amount and size of the pores would lead to decrease in hardness. And in case of cold roll composite, hardness increases due to significant increase in densities of CNT copper nanocomposite. So, we can see that by using microwave sintering, we definitely can synthesize ceramic matrix composite. Along with that, we also can synthesize this kind of metal matrix composites also. And we can do lot of different kind of post treatment to post treatment further to improve their mechanical properties. Okay. So, I think I have discussed enough on this particular topic of microwave sintering and how we can make composite materials using microwave sintering. Okay. And just to show you the fracture study here, fracture behavior here. So, you can see that this copper actually matrix, you can see here how nicely it shows this ductile fracture with lot of nice dimples. Okay. And then at a higher magnification, you can see there is CNT pull out and CNT fracture, and that is the classical composite material failure which is taking place here. Okay. So, with that I would like to end today's class, and in the next class, as you can see in this particular slide, what I am planning is that to discuss the last section, which is basically application oriented advanced composites. So, the first three topics we have discussed, some topics we have discussed in details, some topics we have discussed briefly, but I think you have got a good idea of these three topics. Now, I would like to move into this topic which talks about application oriented advanced composites, and in this I will talk about 4 sectors: space industry, nuclear energy sector, automotive industry and aerospace industry, where various kinds of advanced composites are being used in different applications. Okay. So, I will see you in the next class. I end the class today here. Thank you all.